Welcome everybody to VARI Medical Academy, one of the prestigious NEET and JEE coaching center in Tamil Nadu. I am fortunate to present today the solutions in the three toughest problems in the NEET Physics 2025. These problems belong to the chapter Thermodynamics. Thermodynamics is a very important chapter in NEET Physics and Chemistry because it is a common chapter in physics and chemistry. So your expertise in the chapter Thermodynamics is very essential for scoring more marks in NEET and JEE. And incidentally, the NEET paper of 2025 in physics may be the toughest ever, and some of the problems are really tough, specifically in the chapter Thermodynamics. These problems require a lot of thinking, a lot of time, and lot of previous knowledge before solving. So it is my duty as an expert in thermodynamics for over 4 decades to simplify the solutions to suit the needs of the NEET and JEE aspirant. I am fortunate to present the problems to you. The first problem is about a gas kept in an oxygen cylinder. It is connected with a valve. The valve is open and some of the gas is allowed to escape. After the escape of the gas, the pressure gauge shows a reduced reading. This is the description of the problem. The question is, how much of oxygen was withdrawn? This is a description of the problem. Now I will read the problem. An oxygen cylinder of volume 30 liters has 18.2 moles of oxygen. After some oxygen is withdrawn from the cylinder, its gauge pressure drops to 11 atmosphere at a temperature of 27 degrees centigrade. The mass of oxygen withdrawn from the cylinder is nearly equal to. You have to find out the mass of oxygen. Oxygen is a pure gas, so we can assume ideal gas is valid for this problem. The gas oxygen obeys ideal gas law. Ideal gas law has 5 parameters: P, V, N, or T. R is a universal gas constant. It is given. So pressure of the gas is given. The volume of the cylinder is given. Volume of the cylinder is volume of the gas. The gas occupies the entire volume. So volume of the gas is 30 liters before and after withdrawal, and the temperature of the gas is 27 degrees centigrade. You have to convert it to Kelvin. It is 300 degree Kelvin. Initial moles is 18.2. You have to find out the number of moles after the withdrawal of the. So the final pressure is 11 atmosphere gauge pressure. You should know what is a gauge pressure. So one of the major tricks in solving the problems in thermodynamics is, rather any problem, to have a diagram of the statement of the problem. So the statement described in the previous slide is converted into a schematic diagram. The schematic diagram shows the oxygen cylinder in the beginning, that is initial state, and the final state after some amount of oxygen is withdrawn. It is shown the initial volume is 30 liters, final volume is also the same 30 liters. Initial temperature is 27 degrees centigrade or 300 degree Kelvin, and also the final temperature is same. There is no change in volume, there is no change in temperature, only the number of mole changes from 18.2 initial moles to some n moles at the end. So the pressure gauge attached to the top of the vessel shows the gauge pressure. So gauge pressure has to be converted to absolute pressure and substituting in the ideal gas. Please note P, the term pressure P in the ideal gas equation is absolute pressure. So convert the gauge pressure into absolute pressure by adding atmosphere. In this slide, the calculation details are shown. The first and the foremost thing to be done is to convert the gauge pressure. The final pressure is given as gauge pressure 11 atmosphere, which has to be converted into absolute pressure by adding the atmospheric pressure. So gauge pressure plus atmospheric pressure is absolute pressure. So absolute pressure is to be used in the ideal gas equation of state. PV is equal to NRT. So the final absolute pressure after the removal of some amount of oxygen is 11 atmosphere plus 1 atmosphere is equal to 12 atmosphere. So final absolute pressure is 12 atmosphere against a gauge pressure of 11. The volume is the entire volume of the cylinder. So it is mandatory in thermodynamic calculation. Please note, it is mandatory that the temperature shall be in degree Kelvin. So in this case, it is given as 27 degrees centigrade. So you have to add 273 to convert to Kelvin. So write the ideal gas equation of state. PV is equal to NRT. Substitute for PV RT. You can calculate N. So after substitution of the values of the variables correctly in the equation, we can proceed with the last phase of solving for the unknown. The unknown is the number of moles n remaining after the removal of some amount of gas. The moles of oxygen remaining. So moles of oxygen remaining as per the calculation is 14.544 moles. Initial mole of oxygen is 18.2 moles. The moles of oxygen removed is 3.656 moles of oxygen. So moles of oxygen removed has been found out. It has been converted into mass of oxygen. So multiply by the molecular weight. Please remember molecular weight has a unit. The unit of the molecular weight is shown as 32 generally. So here the unit selected is gram per mole because we are using moles. So molecular weight of oxygen selected is 32 gram per mole. So multiplying the moles by the molecular weight, we get the mass of oxygen in gram. Please note the mass of oxygen is given in grams. You convert it to kilogram by dividing by 1000. The answer is 0.116. The next beautiful problem of NEET 2025 physics is mixing of ideal gases in an adiabatic way. So a chamber is presented, two chambers. A container is presented with two chambers. One is having a volume 2 liters, another is having a volume 3 liters. So one side 5 moles of gas is kept, another side 4 moles of gas is kept. The gases are separated by a non-conducting partition. The initial pressure of one side gas is 1 atmosphere and the initial pressure of the other side gas is 2 atmosphere. This is the initial situation. Now the partition is removed and the gases are allowed to mix and attain an equilibrium. The question asked is, after the mixing of the gas, what is the pressure? That is called equilibrium pressure. This slide shows the schematic diagram of the initial state of the pure ideal gases and the final state of the ideal gas mixture. The initial state is on the left hand side 5 moles of gas occupying a volume of 2 liters and the pressure is 1 atmosphere, temperature is T. On and the right side of the container, the chamber, the gas, second gas is there. The first and second gas are separated by a non-conducting partition. The second gas has 4 moles, 3 liters, 2 atmosphere. Note the temperature is same. The first assumption is the temperature of both the gases are same. This is the initial state. Now the partition is removed and the ideal pure gases are mixed to get an ideal gas mixture. You know the properties of mixing of ideal gases. So there are two facts that you remember. There is no volume change of mixing due to ideal gases and of course the gas occupy the entire vessel. Anyway, second, the enthalpy change of mixing of ideal gases is 0. There is no enthalpy change. And you know the enthalpy of ideal gas is equal to NCP delta T. Since there is no change in temperature, there is no change in enthalpy. So enthalpy change is 0. So the temperature of the final gas mixture is the initial temperature of the pure gas, which is T. So temperature is same before and after mixing. The number of moles are sum of the moles. 5 plus 4, 9 moles. The final volume is 2 plus 3, 5 liters. This is a description of the problem. So in this slide, how to develop the equation to solve the problem is shown. So we use the fact the total number of moles is conserved. So N1 plus N2 is N total. So since gas N1 is the number of moles of the gas 1 which is on the left side. So using ideal gas equation, N1 is equal to P1 V1 by RT. Similarly for gas 2, N2 is P2 V2 by RT. And in the same way for the gas mixture, P final V final RT. RT cancels out throughout. So we give a simplified, we get a simplified equation. P1 V1 plus P2 V2 is equal to P final V final. So substitute the values. See the unit on the left and right side are consistent. So there is no need to convert the units. Consistency of units is maintained. That is one of the important things that you should note in solving problem. So the final atmosphere is found out to be 1.6 atmosphere. So the third problem which we have taken for discussion is we have two piston cylinder arrangement, a closed system. As you know, piston cylinder arrangement is a closed system and you have to be conscious about the first law equation applicable to the closed system. And gas A is kept in one cylinder, gas B is kept in another cylinder. The cylinder diameters or radius are different, or the piston diameter and radius are different. This is the initial situation. Now same amount of heat is added to the gases A and B, same amount of heat. So once heat is added to the system, the kinetic energy of the gaseous molecule increases. They bombard the walls, they bombard the piston. The molecules bombarding the piston push the piston up. So the gas expands. The gas expands, the piston glass does work, the system does work on the surrounding, the piston rises. The piston in gas A is displaced by 16 centimeter, piston in gas B is displaced by 9 centimeter, and the internal energy is same in both the gases. So under this situation, what is the ratio of the radius of the piston? This slide shows the schematic diagram of both the cylinders. On the left side, say gas A is kept, and the right side gas B is kept. So cylinder diameters are different. So diameter A and diameter B, and the external pressure acting is P. So the displacement of the piston due to the heat addition Q, same amount of heat is added, is shown. First cylinder piston gives a displacement of 16 centimeter, second 9 centimeter. So you have to understand, a gas kept in a piston cylinder arrangement is classified as a closed system. Heat is added, work is done by the system, the gas on the surroundings. Work is done by the system due to expansion, and the pressure, external pressure shown as P, is constant. So internal energy of the system is also constant. This is a representation of the problem. So the step-by-step solution of the problem is given. The first step is to write the first law equation for the given system and the given mode of exchange of heat and work interaction. One should realize two things when writing the first law equation. What is a type of system? What is a type of heat addition or work done or by the system? Heat exchange by the system, work exchange by the system has to be clearly noted. So for the given heat addition and work done by the system, for this closed system, the first law equation is delta U is Q minus W. So the major work of writing the first law is over. Now you realize the internal energy change in the gas A is delta U, internal energy change in the gas B is delta UB. Both are equal. Delta UA equal to delta UB. It is given the heat added QA is equal to QB. So combining these three equations, we arrive at the work done by the system by gas A equal to work done by the gas B by comparison. And also you note, as per the figure, the expansion is under a constant pressure of P. For a constant pressure process, isobaric process, the work done is given by W equal to P delta V. So work done for the gas by the gas is P delta VA. Work done by the gas B is P delta VB. Delta V is a change in the volume of the gas. So it is defined, delta V is defined as the final volume minus initial volume. So PVA, P into VA minus V initial equal to P into VB minus V initial. From the above equation, we conclude the volume change. From the volume change, we find out that VA equal to VB. Initial volume get cancelled. So final volume VA equal to VB. So volume is equal to area into length, area of the piston into the displacement. So assuming it is a circular disc, the area is pi d square by 4. Substitute the values, then you get dA divided by dB is equal to 3 by 4, which is nothing but RA divided by RB. The ratio of the diameter is equal to ratio of the volume. It is a simplification step. The answer is dA divided by dB is equal to 3 by 4. So thank you for listening to me. Hope I have made the toughest problems in the NEET Physics 2025, the Thermodynamics chapter problem, possibly in a simple way based on my over 40 years of experience in teaching thermodynamics. If you have any doubt related to thermodynamics, I am glad to help you. Please contact me at the number. We are also conducting test series. We are also ready to admit you for NEET and JEE under offline or online. So kindly contact the number as per requirement. Hope you enjoyed the explanation of the three of the toughest problems in physics, and wish you good luck. And with this knowledge, you will be able to face NEET 2026 confidently.